My name is Grace Lim. This is my Physics 2211 Lab 3 lab report on black holes and orbits. So first part of this lab, the main goal was to find the mass of the black hole by observing the motion of the star. And through observing this motion, the net force can be calculated using fundamental principles of physics, which would allow for the calculation of the black hole, which was found to be 1.39 times 10 to the 34th kilograms. And the purpose of the second part of this lab is to determine what initial velocity a spaceship needs in order to orbit around both a planet and the moon without crashing into them. And this will be calculated by determining the forces on the moon as well as all the forces on the spaceship in order to create position update formulas which allow for the creation of their orbits. And this ideal velocity was found to be 25,000, 0 meters per second. And the assumption is that the only force in the first part of the lab is of the black hole, and the only force in the second part of the lab is going to be the forces present on the moon and the spaceship. And then this other assumption is that the code can perfectly replicate these motions. And then the system in the first part is going to be the star, and the surroundings is going to be the black hole. And the systems in the second part is going to be the moon and the spaceship. And then the surroundings is going to be the planet, the moon, and the spaceships. And the procedure for both parts is going to be very similar, as we're just going to be manipulating the glow script code in order to first find the mass using FG and then to set the initial velocity. For the first part of the lab, in order to find the mass of the black hole, we established some fundamental principles of physics that we use. So the first one that we are going to be using is the Newton's second law of motion and the momentum principle, which shows that the change in momentum is going to be equal to the F net. And then the second part is that we can split up the F net into perpendicular and parallel components and add them to each other. And then the third principle that we're using is Newton's law of universal gravitation. And then first, for manipulating the glow script code, I put in my email, and then I was able to set the gravitational constant as well as take the mass of the star from the lab and then set up the delta t. And then I was able to compute the initial and final momentum vectors just by multiplying the initial and final velocity times the mass of the star, and then I was able to calculate the change in velocity and the change in momentum just by subtracting the final and initial of both. And then using the momentum principle, I was able to find the overall F net by finding the net force in the parallel, and then subtracting that from the net force overall in order to find the F net perp, and then this allowed to find the overall net force by this law. Once I found the net force, I was able to manipulate the law of universal gravitation in order to just solve for the mass of the black hole, and I was able to plug in the net force in order to find the mass of the black hole. But because the position vector, as shown above, is going to be different depending on the time period, I had to take the average of all the masses that were given, which allowed for the calculation of 1.39 times 10 to the 34th kilograms as the mass of the black hole. And then moving on to part 2 of this lab, I was able to use this same fundamental principles of momentum as well as universal gravitation, but I was also able to create the position update formula from using the momentum principle, which allowed for the creation of the third fundamental principle used in this part of this lab. Once these fundamental principles were established, I manipulated the glow script code in order to find the initial conditions for this lab, which is basically the mass of each of the objects as well as gravitational force and the delta t. And then we're trying to solve for the initial speed and velocity in this part of the lab. Once those initial conditions were set up, I first created position vectors for the planet to the moon as well as the planet to the ship and the ship to the moon and the moon to the ship. And then once we did this, we were able to use the law of universal gravitation and multiply that by the position vectors that were found to find all of the forces on the moon, which is going to be the force from the planet and the ship, and all the forces on the ship, which is going to be from the planet and the moon. And when you add them together, you're able to get the overall net force on the moon and the overall net force on the ship. Once the net forces on the ship and the moon were established, I was able to use the velocity update formula to update their velocity, and then from that I was able to use the position update formula in order to update the position and create the correct orbits. And then here are the orbits that I was able to create. The cyan orbit is going to be the orbit of the moon, and then the spaceship is going to be the magenta orbit around the planet, which is going to be the blue dot. And then I was able to do this because I set up my initial velocity to be 25,000 times 0, which allowed for the spaceship to go around both the moon and the planet without crashing into them, and trying to manipulate it to create a figure 8 orbit, although that figure 8 orbit was not perfectly created, but it was able to sustain an orbit over a long period of time. And then lastly, the error in this lab. For the first part, error could come from the fact that the approximations on delta D are just based on one day and not based on a full time period. And then for part 2, a major error is that there's a variety of different initial velocities that would all yield similar answers. But moving on from this, what does this mean as a whole for part 1? So how do the net force and its perpendicular and parallel components differ from the rate of change in momentum and its parallel and perpendicular components? So firstly, although they're mathematically the same, the rate of change in momentum describes a system's motion, so it depends on the change in the motion of the system. However, the net force describes all of the forces from the surroundings onto the system, so they're getting the same mathematical answer, but they're approaching in different ways. And then secondly, if we wanted to correctly predict the motion of the entire system with the black hole, we would do the same thing and we would consider all the interactions and gravitational forces between each object. However, this lab does not consider the gravitational influence of the black hole be the most dominant influence, as its mass is greater than any other, so it would dominate every other interaction, making them all seem very much smaller in contribution wise. But yeah, so thank you guys so much for listening.